All right, open up your book to section 14-8. We're on page 740 in your book. And the title of this section is Mathematical Expectation. The objective here is to calculate the mathematical expectation for a given random experiment. All right, so let's start out with an example so we can understand the basic idea here of what a mathematical expectation is. So we're going to use the example they give us here on page 740 in your book, which they describe some sort of a school carnival, I guess, that you're having. And instead of playing with money, we're playing with points. So there's some sort of point system that you have. But anyways, you have a school carnival game, and a student pays 50 points to roll a die, and you roll the die one time. And then here's the payout for that game. The payoffs for the game are as follows. If the student rolls a 6, then they win 150 points. So they paid 50 to play, they win 150, so overall they won 100 points. All right, they still had to pay the 50 points to play. If they roll a 2 or a 4, then they win 60 points. Again, they already paid 50 to play, so they won 60, a little bit more back than what they paid. And then finally, if they roll a 1, 3, or 5, then they win 0 points. But they still had to pay the 50 points to play the game. All right, so the 50 points is what they have to pay up front, and then these are the winnings. So the question is, what are the expected winnings, or maybe it's losings, depending on how this game is set up here. Let's see what we would expect to happen if we were to play this game. All right, so let's make a table of data here to keep track of some things, and then we'll calculate what our expectation is from that. So I'm going to make one column. My table will be the events that we're looking at. Right, and the events are how the payoffs here are determined. So the first event is rolling a 6, so I'll put that first in my table. The second event would be rolling a 2 or a 4. And the third event is an odd, so it's 1, 3, or 5. All right, so I'm going to just make a table with 3 rows in it here, indicating for me these 3 different events. And then let's keep track of what the probability of each one of these events is. Now we're just rolling a die, so we've done plenty of work with simple probabilities like that, so we should be able to figure out what the probability is. The event of rolling a 6, there's only one 6 on the die, and there's a total of 6 different possible outcomes there in our sample space. So we know the probability of rolling a 6 is 1 out of 6. There's 1/6 chance that that happens. Rolling a 2 or 4, again, there's two sides of my die that contain the 2 and the 4 out of the 6, so that's 2 out of 6. And then finally, for the last event there, that's 3 possibilities out of the 6 possible outcomes there in my sample space, so it's 3 out of 6. All right, so that's my probability of each one of those happening. And now let's look at what the net payoff is. And the key here is that we're using the word net payoff. And by using the word net payoff, we're saying that we're going to take into account not only what you can win, but then we're also removing the cost to play this game. All right, so it's just the net winnings there is what we're looking at, or the net payoff. So remember that we pay 50 points to play the game. And if we roll a 6, we win 150 points. So the difference between those two, the amount we win minus the amount we have to pay, is our net payoff. So our net payoff there for rolling a 6 is 100 points. For the 2 and the 4, you win 60 points. But again, you had to pay 50 to play. So your net payoff there is 10. And then finally for the 1, 3, or 5, the odd numbers, again, you win nothing in that case, and you had to pay 50 points still to play, so your net payoff is you lose all 50 points, negative 50. All right, so now I've got the probability, and I've got the net payoff for each one of those events. So if I take each of these probabilities, I'm going to call this E, that's what we're going to eventually call these, is the expected mathematical expectation here is E. If I take each of these probabilities and multiplying by their net payoff, that should tell me overall what I would expect to end up with as a result of playing this game one time. Or over time, how much I could calculate how much I would win or lose in playing this game multiple times. So for the event of rolling a 6, the probability of rolling a 6 is 1 out of 6, and the payoff for doing that is just 100 points. And again, that 100 includes the amount I paid as well as the amount that I actually win. So I've taken the difference to calculate those net payoffs. And finally, for the 2 and the 4, the chances of rolling a 2 and a 4 is 2 out of 6, and I'm multiplying that by the winnings, or the net payoff, I should say, of rolling the 2 or the 4. And finally, there's a 3 out of 6 chance and of rolling an odd number, and the payoff for that, the net payoff, is a minus 50 points. We lose points if that's the case. Okay, so then the question is, well, what's this turn out to be equal to? Well, we can, I guess we can probably calculate this without a calculator. These are all got the same denominator, so it should be a little bit easier here to add this up. In fact, let's write it that way. This is 100 over 6. This is 20 over 6. And then this is going to be a minus 150 over 6 if we rewrite these all as just fractions here, multiplying those payoffs times that numerator. And so what do we have here? We've got 120 minus 150. That's going to be a negative 30 over 6. Negative 30 over 6, so that's nice. That's actually a negative 5. So a negative 5 points is the expected payoff here. I would expect that if I play this game over time, every time I play it, I'm going to lose 5 points. Now, there's actually no way to lose 5 points in one play of the game, but overall, I would expect that if I played it multiple times, I'm going to lose 5 points every time. That is my mathematical expectation. That right there is exactly how we calculate a mathematical expectation. Take your probabilities of each event for that particular experiment we're talking about, multiply them by their net payoffs, add all that up, and you end up with your mathematical expectation. So here's that property all summed up here then. Mathematical expectation. For n mutually exclusive events, we've talked about mutually exclusive and what that means. That means there's no overlap. That is critical on this. You got to make sure the events that you're looking at have no overlap. And rolling our die, our events were mutually exclusive. The first one was just getting a 6. The next one was getting a 2 and a 4. And the last one was a 1, 3, or 5. There was no overlap there between any of those. You know, if we had said a number greater than 3, and then we had odd numbers, there's some overlap there, because there's an odd number that was greater than 3. So you have to be careful and make sure these are mutually exclusive events. We're going to call these A1, A2, A3, and so forth, all the way up to A sub n. So uppercase A through 1 through uppercase A sub n will be the names of our events, and they're mutually exclusive. And they have a corresponding payoff, and we'll use little a to indicate the payoff here. So little a sub 1 will be the payoff for event big A sub 1, and little a sub 2 will be the payoff for event big A sub 2, and so forth, all the way up to little a sub n is the payoff for big A sub n. And again, it's the net payoff that we're talking about here. So we've got not only the winnings for that particular event, but we also have to account for the cost to actually play this particular a game, or if it's whatever it might be. It might not be a game here that you're playing like we saw, but the cost of actually doing this experiment. All right, the mathematical expectation is then exactly what we just calculated. Take the probabilities of each event, multiplying by their net payoffs, add all that up, and you end up with your mathematical expectation. This would tell you whether or not it's a winning or a losing venture. You can write this mathematical expectation using sigma notation or summation notation. That letter that you see there, that kind of that E-shaped letter there, that's the Greek letter sigma, the uppercase Greek letter sigma. And again, that means that you're summing from k equals 1 at the bottom all the way up to k equals n is our stopping point. And it's just saying you take p, your probability of event a sub k, when k is 1, it would be probability of a sub 1, times the payoff a sub 1. And then you let k be 2 and 3 and 4 and so forth. So this is just another way that you can write a summation of a series here, is using this sigma notation or this summation notation there we call it. All right, a couple things to note here about what we've talked about. First of all, when we talk about these events, it's critical that they're mutually exclusive. We've already talked about that, but it's also critical that you've included all of the possible events. So all possible events are included such that if you add up all their probabilities, probability of a sub 1 plus probability of a sub 2 plus probability of a sub 3 and so forth, you've included all of them, so that means that the sum is 1. Again, if there's anything that you've left off here, then obviously your mathematical expectation is not going to be correct. So you got to make sure that not only are they mutually exclusive, but you've included all of them. All right, and the second thing there is the net payoff. Just like we saw in that first example there, the net payoff is actually the actual payoff for that particular event minus the cost. So when we talk about net payoff there, you've got to consider both of those. If you don't include the cost there, then obviously your net payoff is going to be a little bit inflated. You just got to realize that you haven't included the cost there. Now technically, you could wait until the very end and subtract out the cost from the whole thing. I like doing this as a net payoff, so I've included both the payoff for that particular event minus the cost, and that's my net payoff there. The book is going to use that same notation or same formula as well, so I think it's easiest if we stick to the way the book is going to do it. All right, let's take a look at another example here then. Look on page 740 in your book. Actually, it's on 742 in your book, example 1. It says the basketball toss at an amusement park costs 50 cents to play. To play, you shoot 3 balls. It says if you make no baskets, you win nothing, and you lose your 50 cents. So there's the cost to play the game here, right? Pay 50 cents to play. If you make just 1 basket, you'll win a keychain that's worth a whole nickel, worth 5 cents. But again, it costs you 50 cents to play. So you actually paid 50 cents for a nickel keychain. If you make 2 of the 3 baskets, you win a stuffed animal worth 60 cents. Well, now you're making some money here, I guess, technically, because you paid 50 cents to play, but you got something worth 60 cents. And it says if you make all 3 baskets, then you win a doll worth $2.50. There's the big money there. So you paid 50 cents to play, and you actually got something worth 5 times as much, right? Worth $2.50. The basketball hoop is small, so your probability of making any one basket is 30%. And then the question is, of course, what is the mathematical expectation for the game, and how do you interpret your answer there? All right, so the question is it a winning venture for you, or is it a winning venture for this little amusement park? Probably the amusement park, by the way, is going to be making money. But let's see what our expected payoff is here, or a mathematical expectation. Let's deal with the probability first of all, and tackle it first, and then we'll jump into actually calculating the mathematical expectation. So with shooting hoops, we are either going to make the shot or we're going to miss the shot. There's only one of 2 possible outcomes here. I either make this shot or I miss it, which means that this is actually a binomial probability. So we can use the formula that we learned in the previous section talking about a binomial probability, that we have a nice little formula that we can use to generate these probabilities in. So let's write that down just to remind ourselves of what that little formula is. If you want to find the probability that you make X shots, probability of making X shots, well, we're only taking 3 shots. So our formula was, it's the number of shots you're going to take. So it's 3, choose X, X being the number of shots you want to make, either 0, 1, 2, or 3. And we multiply that by the probability of making a shot. Now they said that the hoop here is small, so our probability of making a shot is only 30%. So that's going to be 0.3 as our probability of making that shot. And we raise that to the power of the number of shots we want to make. Again, we're calling that x here. And then we multiply by the complement of that probability, which would be 0.7, the probability of missing a shot, in other words. And we raise that to the 3 minus x. Go back and refresh your memory of that formula if you need to remember how to calculate a binomial probability. By the way, for this problem, it's a binomial probability. That does not mean for every problem that you're going to see here in this section that it's always going to be a binomial probability. You got to think about how am I going to calculate the probability for this problem, and then go about calculating it. All right, for this one, it turned out it was binomial, so here is our formula. But you're going to need to know those other techniques we've talked about throughout the chapter to help us know how do I find the probability here. All right, so this little formula here is going to be helpful when we go to fill in our table here for probabilities. It's not quite as easy as the rolling the dice example. I didn't need this to figure out the rolling the dice example. I knew that there were only 6 outcomes for rolling a die, and I could count up how many outcomes were in each event. It was really easy to calculate. This one I got a little bit more to it. All right, so let's make our table. I'm going to make the same table that we saw on that first example. We'll keep track of our events. And our events are how many shots we're going to make. We're taking 3 shots, and so I'm only going to make either 0, 1, 2, or 3 shots. And then let's keep track of our probability. That's why we did the work up above there, was first to figure out how am I going to calculate these probabilities. So we're going to grab our calculator here in a second, and we'll fill in that table, or that second column of the table here. Let's go ahead and fill in the net payoffs, because we can do that without our calculator, I think. So your net payoffs, again, you're paying 50 cents to play the game. And so think about what your payoffs are going to be for each of these. If you make 0 shots, it says that you win nothing. So it's going to be 0 minus your 50 cents that you paid to play the game. So that's a negative 50 cents, a minus 50 cents. You lose 50 cents. It said that if you make 1 shot, then you win this keychain that's worth a nickel. So your winnings is 0.05, a nickel, minus the 50 cents that you paid to play the game. So that's a minus 45 cents is what we're going to lose by making only 1 shot. Now, if you make 2 shots, making 2 shots, you won this stuffed animal here worth 60 cents. So we have a 60 cents stuffed animal minus the 50 cents that you used to play the game. Means that you win this time 10 cents. And then finally, for the last row on our table, this is the big winnings that you win this doll that was worth $2.50. If you make all 3 shots, you had to pay 50 cents to play the game. So your net winnings is $2. All right, so again, our net payoffs, we're taking into account how much we've paid to play the game, as well as what we win if that particular event happens. All right, so let's grab our calculator and have it help us come up with these probabilities here. So go ahead and grab your calculator and let's try this out. All right, so on your calculator, let's just put into y1 the equation. We're going to go over to our table to help us come up with these values here. So in y1, we're going to put in 3 choose x. 3 choose x. And then the probability of making a basket is 30%, and we're raising that to the x power for x shots that we're going to make. And then we're going to multiply that by the probability that we miss, which is 0.7, and we're raising that to the 3 minus x power. All right, right there is our calculation, our binomial probability here for calculating making x shots out of 3 total. All right, so if we go to our table, set up, and start out at 0 and go by 1, that would be just fine there. There's our values. All right, in fact, I'm just going to grab a picture of that. And we can fill in our table now. Just trim this down a little bit, and I'll slide it over here so I can see it. All right. So let's fill in those values. So if you make 0 shots, there's a 34% chance that's going to happen. Actually, let me write it this way. I'm going to write it as P of 0 equals that. You don't necessarily have to say P of 0, but just so we're clear on what we're doing to come up with that. We're taking that equation up there at the top, plugging in 0, and we get 0.343. And then P of 1 is equal to 0.441. P of 2 is equal to 0.189. And P of 3 is equal to 0.027. It's about a 3% chance that you're going to make all three. So not a very good chance at this game. All right. That's the work that we need to have in order to come up with our calculations, or that's what we need to consider to come up with our mathematical expectation. So now let's go through the work of finding our mathematical expectation. What is E equal to? The mathematical expectation, we take the probability of the event and multiply it by its payoff. So we have 0.343, and we're multiplying it by a negative 0.50. And we add that to the 0.441, and we multiply it by the negative 0.45. And we take the 0.189, and we multiply by the payoff of 10 cents. And then finally, I'll have to come down here and fill that in. Take the probability of making all three shots, which is 0.027, and we multiply it by our payoff of $2. All right. So now with that, we can calculate what our mathematical expectation is. Let's go back to our calculator and do that. Now you got a couple of ways that you could do this. I'm going to show you how to use, you can just do this right on the home screen. You know how to do that. I'm going to show you how you could use list to do it. With only 4 things in my list, I might be spending a little bit more time doing it this way than if I just did it on the home screen. But if your list gets really long, maybe I've got 10 or 20 events here now, using list to do it might speed up that calculation for you. Okay, so let me show you how you could do that. Again, what I need to do is get this data into a list. So we did that in the previous lesson. But just to remind you, you'll go to your Stat menu, and I'll go to Edit. And I'm going to plug in my 3 events here, 0, 1, 2, or 3 shots that I'm making. And then remember, you can go up to List 2, and you can say to take Y1, go to your Variables menu, go over to Y Variables, Function, Y1, and then in parentheses, put the list 1, second, and then the number 1 there. So I am evaluating Y1 at the 4 values that I just dumped into list 1, is what that's saying to do. So there's the values that we just put into our table there up above. Over in list 3, what I'm going to do is I'm going to actually put in the payoffs here, the net payoffs. So I'm kind of recreating that table that I had on the board there, really on my calculator is what I'm doing. So now the payoffs, again, it was negative 50 cents there, right, for the first one. Negative 0.5. It was a negative 45 cents for the second one. It was 10 cents is what you won for making 2 shots, and it was $2 that you won there for making all 3. This is the net payoff that we're putting in that table there. All right, so now what I can do is I can actually take list 2 and multiply it by list 3, and then sum that up. You can do that over on the home screen, but just so you can see it all happen here, I'm going to do it still in my list editor. If I go over to list 4 and go up to list 4's name, I can tell it to take list 2 and multiply it by list 3. And it'll just multiply corresponding entries together and give me this result right here. And now all I need to do is sum that up. I've now got all the products. I just want to sum up that list. So over on my home screen, I can tell it to sum this up. I go under my list menu, second list, go over to math. Option 5 there is to sum, and I've dumped in the numbers that I want to sum up in list 4. And press enter, we get a negative 0.29705. Negative 0.29705. Actually, I'm going to grab a picture of that. And in fact, maybe I'll even grab a picture. Let me put this in my slide first. Maybe I'll even grab a picture of my list, just so you can see that in the slide as well. So So these are my lists. Let's move over here so that's off there. Let me grab a picture of that too. All right. Now we can fill in what our mathematical expectation is. Our mathematical expectation, we said, was the negative 0.29705. So this is equal to a negative 0.297. Again, make sure you got 3 decimal places in your answer there. If you want to list all those decimals, you can, but I need at least 3 of those. So what does this actually mean? This is how much I'm expecting, in this case, to lose every time I play the game. I'm going to lose approximately 30 cents every time I play the game. You lose 30 cents. That would be in dollars, 0.30 is what I'm saying there. You're losing approximately 30 cents every time you play. Now, technically, you're losing 29.7 cents, but I'm rounding that near a cent there when I write that out. But you lose 30 cents approximately every time you play the game. That's what that number actually means. All right, that right there is our mathematical expectation. That's our calculation that we do to find a mathematical expectation. You got to know how to calculate the probabilities of each of those events, which is what we've covered throughout this entire chapter up to this point. And you multiply by the payoffs, the net payoffs for each one of those events. You add all that up and you got yourself a mathematical expectation.